Hi, and welcome to your video lesson for Chapter 2.2. Alright, here we go, AP Statistics. We're going to talk about density curves and normal distributions. This is when we start getting a lot more mathy. Alright, so we're going to look at locations of mean and median on a density curve. Estimate some areas. In a normal distribution, we're going to talk about what a normal distribution is. Look at z-values for z-scores, right? We talked about that. And then we're going to find proportion of values in a specified interval. All right? And then also determine whether a distribution is approximately normal, looking at graphs and numbers. So there's a lot in this, okay? Hey, whenever we're looking at quantitative data, you really need to do these things. All right, remember your socks. Okay? And we're going to look at a numerical summary as well. And then look at this overall pattern. And sometimes we can describe it using a smooth curve if it's nice and symmetric or follows a certain pattern. All right. There's our definition of a density curve. You can also find this in your text. The most important thing about a density curve, in my opinion, is that it has an area of exactly 1 underneath it. That is so that it can be expressed in terms of probabilities, right? Which are always between 0 and 1. All right, if we were to look at this particular histogram, okay, it can be described by a smooth curve. It looks approximately symmetric as well. All right, when we're going to describe these density curves, we're going to apply measures of center and spread. All right, so we'll be able to look at the median, the mean. We'll look at standard deviation, interquartile range. All of these values apply to density curves as well. Really important, the median and the mean should be the same for a symmetric density curve. All right, it should be exactly at the center. Even more importantly, the mean of a skewed curve is pulled away from the median in the direction of the long tail, right? So if you have a lot of data over on the right-hand side, right, that's going to push your mean out to the left. And there is a good picture of that right here, right? So if we have something that is symmetric, median and mean should be in the same spot. When we have this skewed data, right, over here, we have some data that is skewed right. And what happens is the median becomes a better measure of center because the mean tends to get pushed out towards the tail. Give me a little reading time. I don't feel like I need to read that to you. We actually do, it is important for us to mention, we distinguish between the mean and standard deviation of our density curve, right? That's our idealized distribution of the data from the actual distribution of the data. And the way that we'll distinguish that is mainly using a different notation. So you notice that we use the notation x bar before, right, to describe our mean. And now, if we're talking about a density curve, we're actually going to use the Greek letter mu, right? So that's that funky looking M thing, right? And then our standard deviation, we were using S sub x for our standard deviation. Now, if we're going to use it, or if we're going to describe standard deviation of a density curve, we're going to use that symbol there, sigma. Looks like a cursive O, possibly. All right, looking at normal distributions. It is particularly important. It is super important. We can generate all kinds of wonderful things, probabilities, find percentages of data within certain ranges, marked by quartiles. We're going to be able to do so much with this normal distribution, right? With this normal curve. All right, and we describe it by giving its mean and its standard deviation, right? And you can see these two different curves. They look different, but they're both normal curves, right? Being described by mean, mu, by your mean. Right, mean and your standard deviation, right? Okay. We've already talked about that, right? We've talked about the mean of a normal distribution being the center, right? Because it is a density curve, right? And we're going to look at this, the second bullet, right? It turns out that they call it change of curvature points. For those of you that have taken calculus, it turns out that those are our inflection points. So our standard deviation, our standard deviation should be occurring at our inflection points. And we'll have a look at that here in a moment. All right, super important. If you see this, it is assumed it is a normal distribution, and the number in place of mu, you have to assume just because of its location in this notation that we're talking about the mean, and that we would assume that our sigma, right, is our standard deviation, and that is standard deviation just because of the location. Just the same way that if you get an ordered pair, right? So if I get the ordered pair 2, 3, it's assumed that I'm talking about an x coordinate of 2 and a y coordinate of 3. Very similar. And you can read that why these normal distributions are important. You'll definitely get to know just how important they are as we go through this course, because as it says in the last bullet, statistical inference, most of them are based on normal distributions. There are a couple other distributions that we'll learn about, but we will depend a lot upon normal distributions for that. And why is that? Because we're able to represent different areas as probabilities. We'll get there. Our 68, 95, 99.7 rule. Every normal curve has this in common. All right? So what's going on here? All right, what it means is that, so 68% of the data is within one standard deviation of the mean, right? That's what that says. So if we assume a mean value here at, wow, that wasn't a very straight line. If we assume that there's a mean value here at 0, what we are saying is that, and also notice, this right here is technically our first inflection point. Right? And so in between here, right, this is one standard deviation. This is 68% of the data is within that range. And then if we look at the range, 2 standard deviations away, right? So this is our next inflection point. So between here and here, we're looking at 95% of the data. Okay, and then 3 standard deviations away between here and here. This is 99.7%. So that's the picture of it. So based on these things, you're able to get a lot of information based on this rule. It's also called the empirical rule as well. And I'm not sure if they're mentioning that, but it can also be called the empirical rule. All right, the standard normal distribution. So all normal distributions are the same if we measure in units of size sigma, or standard deviation, from the mean mu as center. All right? So this is what we're looking at. We're looking at the standard normal distribution. It makes sense that 0 is in the middle, right? That 0 is right here in our center point. Our center point is where our mean is, right? And if we're looking at this, right, if we're talking about how many standard deviations we are from the mean, it makes sense that we would have 0 in the middle because we are exactly 0 standard deviations from the mean, right? So if we're looking at this standard normal distribution, right, what we're doing is we're calculating z-score. So we're looking at standardized values of the data which gives us a data points relationship in terms of distance from the mean. All right, and that's what we talked about when we were calculating these z-scores in 2.1. Except for now, we're going to be calculating them really with this normal distribution in mind. And when we do, we will use this formula, which you will have forever ingrained in your brain, right? Our z-score is equal to x minus mu divided by sigma. We're going to look at this standard normal table, all right? Also referred to as table A. The table of areas under the standard normal curve. The table entry for each value is the area. And we're going to work a bunch of problems where we're going to use that normal table. And I'll be printing some of those out for you all so that you can have them and use them. We're going to actually do a bunch of exercises using these standard normal tables in class. All right, so we'll give those tables to you, and you'll be able to see the bigger picture of this. This isn't the best way to show this to you, so we'll work example problems in class so that you can see what's going on. We're using this table to find any value, right, that is less than 0.81 standard deviations from the mean, right? Less than 0.81 standard deviations, really above the mean in this case. All right, so all right. So this is going to be the steps that we're going to use to answer questions about areas, all right? We always have to draw the distribution. So you draw tons and tons of normal curves as you go through this. Always draw it, and then always label our values of interest. Please, please shade the area that you're trying to look for, right? That proportion is represented as an area. And we'll get into how to do that, see lots of examples in class as well. Then you're going to perform your calculations, okay? You absolutely must, when you calculate your z-score, you can't just put that in your calculator and spit out an answer. You have to actually substitute those values in for x and for mu and for sigma, and show those substituted values, and then also show your calculated value. All right, you can use your calculator to get that proportion, or you can use the table, and you'll see how we do that tomorrow. And that's okay, but you need to include all those things. You need to have a picture of the distribution. You need to have your values that you're given in the problem clearly labeled. You must shade your area of interest, what you're using your table or your calculator to find that proportion. You have to show that, and then you also must show your substituted values for x, for your mean, and for your standard deviation. You can also work backwards. So you can use the table, so you can be given a proportion, and then find a z-score from that proportion. All right? The same thing you would do. You would do the exact same thing. Always draw that normal curve. Always label the mean, standard deviation. Maybe you have something unknown in there. Make sure that you identify the shaded region that we're talking about in terms of this proportion, all right? We're going to then perform our calculations. You really, really, really have to show all of your calculations as you do these. And as I said, I'm going to model a bunch of these for you during class. All right, also, if we are given some sort of data set, we're able to assess normality. I'll show you how to do that with your calculators. You can get a normal probability plot. You normally are going to need all of the data for that in order to calculate that. And that is going to be another thing that we will get done during class. It's very simple to do. It's all calculator work and really no work on your part. You just need to be able to interpret the graph that the calculator outputs. And that's it as far as an overview goes for this lesson. You should be ready now for us to work on some specific problems. I'm going to show you some methods and show you how to get technology to help you through that. Thanks for watching. See you tomorrow. We have tons of work to do.